The mean value theorem is one of the most important theorems in calculus. It has sparked countless discoveries and is a very useful tool for a mathematician to have in their tool belt. In this video, I would like to cover a proof for the mean value theorem and provide helpful visuals along the way. For the sake of this video, I will assume you are familiar with the concept of continuity and have a little calculus knowledge. The theorem is as follows. If f is continuous on the closed interval a, b and differentiable on the open interval a, b, then there exists a point c in the closed interval such that f prime of c is equal to f of a minus f of b over a minus b. Before we construct our proof, we want to establish two useful facts. The first fact being that if f is continuous on the closed interval a, b, then f has a maximum value on a, b. To help understand this, let's look at a graph and plot our two arbitrary values for a and b. It doesn't matter where we place our points, but we will place them on the x-axis for simplicity. Now, any continuous function we draw between these points will always have a maximum value. It doesn't matter how much we bend, stretch, or deform our function. As long as we can draw our graph in one continuous line without lifting our pencil, there will always exist some value x in between a and b such that f of x is a maximum value. Notice how the continuity of our function is crucial here. For an example y, let's look at this graph, which is discontinuous because of its asymptotic behavior at x equals 0. Because of this asymptote, f has no maximum value, as we can select ever-increasing values of f near x equals 0. Now let's look at the second useful fact. If f is differentiable and has a local maximum at f of c, then f prime of c is equal to 0. Let's recall that for f to be differentiable at c, then the limit as x approaches c of f of c minus f of x over c minus x must exist. Now, since this limit exists, this means that the left-sided limit must be equal to the right-sided limit. Let's take a look at a graphical interpretation of this problem. As an example, we will define our function f as 2 minus x squared. Notice that we have this value c and its corresponding value f of c, which is a local maximum for our function. To prove the derivative is equal to 0 at c, let's first examine the left-sided limit. Let's select the value of x from the left of c while also graphing f of x. As we move our value of x closer to c from the left, f of c will always be greater than or equal to f of x. Subtracting f of x from both sides of this inequality gives us f of c minus f of x is greater than or equal to 0. Similarly, since we are choosing values of x to the left of c, c will always be greater than x. Subtracting x from both sides gives us c minus x is greater than 0. Now if we divide f of c minus f of x by c minus x, we have a non-negative number divided by a positive number, which will result in a non-negative number. Combining all this gives the result that the limit from the left is greater than or equal to 0. This can be nicely visualized by looking at the tangent line of the points to the left of c. As we move our point closer to c, the slope of the tangent line always remains greater than or equal to 0. We can now apply the same process to the right-sided limit. As we choose points of x to the right of c and move them closer to c, the value of f of x is always less than f of c. Subtracting f of x yields f of c minus f of x is greater than 0. Because we are selecting points to the right of c, c is less than x. Subtracting x gives c minus x is less than 0. Dividing these two inequalities, like we did with the left limit, gives us a different result this time. That is, f of c minus f of x over c minus x is less than or equal to 0. So, we can conclude that the right limit is less than or equal to 0. Again, this is visualized nicely by the slope of the tangent line to the points to the right of c. Notice that that slope always remains greater than or equal to 0. Now, we can combine the two inequalities we got from this process. Recall that since f is differentiable, the overall limit must exist, meaning that the left limit must be equal to the right limit. With our inequality above, we can conclude that the only value that both the right and the left limit can be is 0. Therefore, the overall limit must be equal to 0. And thus, we can conclude that if f of c is a maximum value, then f prime of c is equal to 0. When you're trying to prove a theorem in math, sometimes it's useful to prove a more specific version of the theorem, and then extend it to a more general case you want to prove. We will use this technique to prove the mean value theorem. But first, the more specific version we need to prove is called Rolle's theorem. The theorem is as follows. If f is continuous on the closed interval a, b, and differentiable on the open interval a, b, with f of a equal to f of b, then there exists some value c in the open interval a, b, such that f prime of c is equal to 0. The proof for this theorem is actually quite simple if we utilize the two facts we just proved. The first fact being that if f is continuous on the closed interval a, b, then f has a maximum value on a, b. The second fact we proved was that if f of c is a maximum value, then f prime of c is equal to 0. Now it seems like we're done and we've finished our proof because we have a value c such that f prime of c is equal to 0. However, there is one specific case we need to consider. What if f of a or f of b is the maximum value? Notice that we run into a problem when we look at f prime of a and f prime of b. Since f is differentiable on the open interval a, b, f prime is not defined at a or b, and we cannot conclude that f prime of a or f prime of b is equal to 0. But there's a way to get around this. Let's take a look at a graph where f of a or f of b is our function's maximum value. One of our assumptions for the theorem is that f of a is equal to f of b. Thus, they are both maximum values of f. Therefore, any continuous graph we draw between these 2 points must not exceed this line. If our function dips down from f of a, it must curve upward to meet f of b. Hence, we have some point in between a and b that is a minimum value for f, at which point f prime is equal to 0. We have one last case to consider. What if our function is the straight line segment from f of a to f of b? Well, if we draw a point and its tangent line, we will notice that f prime is equal to 0 for all points in between a and b. And we're done. We have proved Rolle's theorem. Now, we will use Rolle's theorem to prove the more generalized mean value theorem. We are now going to prove the mean value theorem. To prove this theorem, we will create a new function h of x. Let's define h of x to be equal to f of x minus f of a minus f of b over a minus b times x. Let's first look at a quick fact about this function. Since f of a minus f of b over a minus b is a constant, multiplying it by x will give us a continuous indifferentiable function. This implies that our function h is also continuous indifferentiable, because h is the sum of two continuous indifferentiable functions. With this out of the way, let's examine a couple graphs. In red, we will graph f of x. Now, let's select our arbitrary values for a and b and plot them on our graph. Additionally, let's plot their corresponding values f of a and f of b. Now, in yellow, we will draw the line passing through f of a and f of b. Notice how this line can be represented by the function f of a minus f of b over a minus b times x. Looking at our graph, we can see that these two functions intersect at the values of a and b. This allows us to write these two equations. Now we can move everything to the same side of the equation and get this as a result. The key observation to make here is that these two equations are equal to h of a and h of b respectively. Thus, we know h of a and h of b are both equal to 0. Let's visualize this on the graph by subtracting our yellow function from our red function. The result is h of x, which is in pink. We can clearly see that h is equal to 0 at a and b. Since h of a and h of b are both equal to 0, we know that h of a is equal to h of b. Now we can combine this with our previous conclusion that h is continuous on the closed interval a, b and differentiable on the open interval a, b. These two facts about h allow us to apply Rolle's theorem to h. Thus, we have some value of c between a and b such that h prime of c is equal to 0. Recall that this is how we defined our function h. Taking the derivative of h gives us h prime of x is equal to f prime of x minus f of a minus f of b over a minus b. Now we can plug in c to this equation. Because h prime of c is 0, we get 0 is equal to f prime of c minus f of a minus f of b over a minus b. After simplifying, we get f prime of c is equal to f of a minus f of b over a minus b. Let's examine this visually. If we bring back the graph of h and mark our value of c, we can see that h prime of c is equal to 0. Now, we will transform our graph back into our function f and redraw our line between f of a and f of b. Now, if we draw the tangent line of the point f of c, we can see that this line is parallel to our line between f of a and f of b. Therefore, our conclusion makes sense graphically. The mean value theorem has been used to prove countless results in calculus. So much so that I would say it is the most essential theorem in all of calculus. To stress this point more, I would like to leave this problem as an exercise to the viewer. Can you use the mean value theorem to prove that if f is differentiable and increasing on the open interval a comma b, then f prime is greater than or equal to 0? Good luck, and thank you for watching.